Okay. Hello everybody, good afternoon. Today my FISP is based on this topic, Adaptive Stable Neural Network Control, applied specifically for nonlinear systems. This project is based on a book called Adaptive Stable Neural Network Control. Basically, in this project and in this talk, we are going to see how we can use the neural networks to perform adaptive stable controllers. Sometimes maybe some approximations like neural networks are employed in many ways for classification, pattern recognition, any other applications. But when we talk about control, we need more strong mathematical properties as stability in order to create good controllers. So for today, we have the next outline. We have a small introduction about what is the importance of adaptive control, the use of neural networks on this kind of control, and how we can use both strategies, I mean neural networks and adaptive control, to create more stable systems. Then we are going to go deeper about the different kinds of neural networks that we can employ to create adaptive controllers. And in fact, there are many kinds of neural networks, but we are going to review the most important, at least for adaptive control. Then they are going to talk about how we can apply these neural network controllers to CISO systems. Here there are very different ways to propose your controller in order to reach your desired results. I mean, there is not only one possibility. And in this section, we are going to talk about something called integral Lyapunov function. That is a way that we can create or define the control law for our system, employing different Lyapunov function, different kind of Lyapunov function that has some properties, especially for the linearization part. Then we are going to talk about adaptive control for non-affine systems. In particular, these kind of systems are very interesting in the sense that the inputs are not linear, are combined with all the systems. So we will have many challenges in order to create or design controllers that could be adaptive and works properly. Finally, some conclusions and future works about how we can apply this technique. Okay, so let's start about the definition of adaptive control. Adaptive control could be considered a control strategy where the controller should adapt online to the system directly to the system dynamics to reach the desired set point. Here we have two important words: adapt for adaptation and online adaptation. It means that you don't have any previous training stages for defining the behavior of the system. I mean, you are running in the middle of the process with the performance of the controller. In that sense, the adaptive controller should deal with external disturbances and parametric uncertainties of the process. A real process has many uncertainties, many disturbances that affects the performance of the system. The adaptive controller should be capable to adapt to these disturbances and reach the desired control output. And another part, because it's adaptive control, we don't need a priori knowledge of the process. In some processes that are very complex, it's very difficult to know or obtain any information valuable to develop a specific controller to reach the desired set. Okay, so this adaptive control could be performed by different ways. Basically, the adaptive control should estimate in some way the dynamic behavior of the system. And for estimate this behavior, you can employ different mathematical tools. For example, splines, linear regression, whatever tool that you can imagine. But we have the neural networks. Neural networks are nothing new, are about 1960 when the first neural network algorithm was proposed. Basically, the neural network works, in our case, as a nonlinear function approximation based on a chain of simple neurons. Here we have an example of a simple neurons. This neuron has 3 inputs, has a weight function. In this case, this weight function is evaluated by the summation of all the inputs, and this will generate as an output. It's important to note that that each of the inputs has some weights, weight 1, weight 2, weight 3 in this case, which will be updated at every iteration of our neural network algorithm, or in the common sense, these weights should be trained previously offline using available data of the process. For example, for classification of, I don't know, colors, you need to train your neural network to these weights, differentiate, for example, between red and blue. But for this, you need previous data and load this data and run many algorithms to train and find the optimal values. Here with adaptive control, we don't have this possibility. We need go controlling the process on the way. We consider in this moment we don't have any kind of training. The neural networks has some advantage, but it has some challenges. In the advantages, there are highly parallel structure, could be in hardware implemented with different kind of algorithms. In controls, could be employed for system identification and control. But one limitation that we have with neural networks, and in general for this kind of control, is that these controllers used to be locally stable only. I mean, only between a compact set of convergence, according to the set point that we are going to control. This is something important that we are going to consider during this presentation. Okay. So, if we want to talk about stable adaptive neural network control, applied particularly to nonlinear systems, we have the following control loop. As we can see, we have the nonlinear system, we have a control loop, any kind of control loop, and we have this block here, the inverse of the system. Normally, for example, for the feedback linearization scheme, you need to know very well the parameters of the system in order to cancel the nonlinearities of the system. For nonlinear systems in controller form or nonlinear system with a good parametric identification process, there is no problem and the feedback linearization could be employed. However, not all the nonlinear systems could be identified in good ways, and you don't have a good knowledge about the constants and parameters of the process. So that this inverse response of the system, it's that we are going to estimate employing the neural networks. What is the main idea here? We have some dynamic here, nonlinear dynamic. We want to cancel or eliminate these nonlinearities. We estimate these nonlinearities using a neural network. In this case, this neural network emulates that behavior. For those, we need the states of the system. We can use directly measure of the states if are available. If they are not available, we need to build a state observer in order to get the information required for the neural network. These states could be employed too for the control law. It depends of the control law that you are going to design. Points important, the system is locally stable between a domain omega c. That's very important because all those adaptive controllers that we are going to talk about today are locally for a compact set. In this case, we are going to define this set omega c. So, this study is based basically on this book, A Stable Adaptive Neural Network Control from Dr. Tao Zhang. This book has some adaptive control strategies that employs the neural network in order to estimate the inverse behavior of the system. There are many kind of techniques. Today we're going to review most of them that are present on the book, and for different kind of nonlinear systems. Okay. So we need some mathematical tools or preliminaries in order to understand and go better with these adaptive control algorithms. The first one are something about vector norms and matrix norms. The P norm for vectors, induced norm for matrices, and the Frobenius norm. Basically, are the norms that we are going to employ in order to calculate or estimate the behavior of the system in between the update loss and between the estimators of neural networks. For the vector norms, particularly, we are going to use the L2 norm. Is the most common norm in the case of vectors, and is employed wide in all the control schemes. Okay, so we are going to introduce another concept. In this case, this concept is the sliding surface for tracking error. This sliding surface basically is a smooth smooth error vector, which has a better control in this case for tracking applications. The tracking applications should be more challenging because you have to follow a pattern. Your system, your output, should follow a pattern or a signal. In regulation task, you only have to reach one point, and you can, design different kind of controllers, but only for this point. Here you have different points that you need to reach. In this case, this sliding surface is based on this equation. This equation basically, it's a polynomial for the error. This polynomial is a Hurwitz polynomial, and this polynomial is convergent between the omega c subset. So we are limiting our control, in this case, to a specific part or a specific point of operation of our nonlinear system. Okay. We have another preliminary mathematical things. For example, Lyapunov stability. We are going to use the Lyapunov stability to determine the stability of the loss, control loss. Lasalle invariance principle, Barbarat lemma, the mean value theorem, that are in all the book in order to determine the behavior of the closed loop system in order to evaluate if it's stable or not stable. Okay, so now these are some preliminaries, mathematical preliminaries. Now we're going to talk about the neural networks itself as the tool to estimate this inverse behavior of our system. Basically, we're going to deal with two types of neural networks. The first one are linear parameterized neural networks. A linear parameterized neural network is that one here. Basically, the neural network works as a function estimator, a function g, in terms of some weights, w, and zeta. Zeta for us is the input vector of our neural network. And s, in this case, is the basis function that our neural network is going to employ. This base function will be clear in the next slide. Okay. The first type of neural network to be analyzed is the radial base function neural network. Basically, the structure of this neural network is the structure that you see here. Here we have the vector zeta with the inputs. We have one output, in this case will be our control action. Here we have some weights that will be updated at each iteration of our control loop. And here we have some basis function. According to the choice of this basis function, our neural network will have a different name. If this basis function is a Gaussian function, it's called radial base neural network. In this case, these functions basically are defined. The function s is defined in terms of the input, and basically each neuron behaves as a normal distribution. So the normal distribution has a mean and has a standard deviation. Those are alternative formulations of this equation, but are equally valid for this network. In the examples of today, we are going to employ this formula that we have here. Okay. This is a basic neural network, the radial base. Now we are going to talk about the high order neural network. High order neural network because we can use a huge number of neurons. Neurons are those ones. And those neurons basically help us to get a better estimation of the behavior of our system. So now, in this case, this high order neural network that is proposed in the book basically has an input vector zeta, has an output in terms of the weights w, and the basis function that ponderates these inputs, it's a little different. In what sense? If you see the first neuron, it's connected to the raw inputs itself, zeta 1, zeta 2, zeta n. Then we have this array, zeta squared, zeta 1, zeta 2, zeta n squared, and here we have the generalization of the algorithm. It means more neurons, you evaluate the inputs and all its possible combinations. That's the main idea of this high order neural network. Evaluate the inputs and its possible combinations. Here is defined how we can expand this network according to the number of neurons that we are going to define. Okay, so now, we said previously that neural networks need some kind of previous training in order to estimate, classify, compensate a dynamical behavior, classify a pattern. But we said, in addition, that we cannot do in adaptive control previous training of the system. So now we need tuning algorithms or update laws, as we can call here for the neural network, that are based for the high order neural network, in this case called HON, and the radial base function RBF. So here we have two possible laws that we are going to employ to update these weights that we have here. In this case, this is a basic robust tuning algorithm. Those techniques or those update laws basically makes a ponderation from the current W of the current weights and ponderates using the radial base function, this ES is the sliding surface term, this delta omega is a tuning parameter, just like a learning rate of our neural network. We have this gamma, this is another tuning parameter that we could employ. The advantage of this kind of tuning algorithm is that they are robust and stable. The book has a big demonstration about how this law is stable on closed loop. But we can have another algorithm, in this case the projection algorithm. This algorithm basically is when you know previously the boundary or the maximum boundary for your weights on your neural network. I mean, for example, your weights cannot surpass 10, 5, and a specific value. In that sense, this algorithm could be employed if, for example, if it's less or equal than your value, you only rise up your coefficients, your W values. But in the other case, when you reach the desired value, in this case the desired value is given by the norm, just have a different ponderation. That's the big idea of this tuning algorithm. Advantage, work online, both of them. We don't need previous training. That in that sense we can employ for adaptive control. And both algorithms belongs to the L infinite norm. It means has a superior limit. This weight cannot be unbounded itself, and has an initial condition W0. This initial condition is very important because if we start with a bad initial condition, probably our algorithm at the beginning will have difficult to converge into the desired closed loop behavior. Okay, this is some kind of neural network that we can employ. Then we have the multilayer neural network. The multilayer neural network is another approach. This is the most common approach of neural network that you could find. In this case, multilayer because has input layer, and many hidden layers itself. This is the input layer, the output layer, and here we have a hidden layer. If we have hidden layers, it implies that we need more weights for each layer. I mean, we have the W weights for the output layer, but because we have this inner layer has these weights V. These weights V will be pondered in this case by a basis function. In the case of multilayer neural networks, this base function used to be the sigmoid function, but you could employ different kind of functions. I mean, hyperbolic tangent, and among others functions you can employ. So this is the most common neural network, and in our case is good because we can extend any kind of hidden layers, any kind of neurons, in order to obtain a better result or better approximation. But we have to deal with something else. If our network is very big and we have online adaptive control, probably the computation time couldn't be enoughly fast to converge or give the desired response. So we have to deal between the number of layers, number of neurons, and the computational power that we have. Maybe today is not a huge issue, but 10 years ago, for sure, it's a problematic situation. Again, we have tuning algorithm for the multilayer neural networks. In this case, we said that we have two layers, the output layer and the input layer. Here, we have a variation of backpropagation algorithm. The backpropagation algorithm is the most usual algorithm for update or tuning the neural networks. Here we have W, here we have V. It depends, in this case, of S, the radial base function, the current weights, the sliding surface. In this case, the sliding surface has a crucial role in our control because all our controllers include this sliding surface in order to perform a better tracking control. This is one alternative, the modified backpropagation. There is another one, weights algorithm. It depends of the problem that you have. You could change, you could switch between different controllers. Okay. So now, the neural network itself only will estimate our desired behavior. I mean, not the desired behavior, sorry. We're going to estimate the nonlinear behavior of our system. This is the main purpose of the neural network. But we need to design our feedback control law that will compensate the nonlinearity, that make use of this neural network of these two. In this case, the basic feedback control law is based on the controller form, and this is the classic feedback linearization technique for linearize the system. In this case, the feedback linearization requires that you know A and B. Probably you don't know A and B for your system, so you will have a problem, are unknown. And for sure, your system will have disturbance. In this case, you have a disturbance here in addition. So many parameters of the dynamic that are unknown and you should estimate. So those parameters are that the neural network will going to estimate A, B, the disturbance, and will consider into the desired control loop. Again, this control loop is into the compact set omega c that we define for each problem. So there are some assumptions. In this case, the desired trajectory is bounded because you have a bounded operation range. This is basically your desired sliding surface for the error. Your control input, this UV, for us, will be that one that we consider at the beginning of feedback linearization. A priori, we know the sign of V. In general, this sign of V is assumed that is bounded between two values, v1, v2, but we don't know these boundaries in most of the cases. How bigger could be the magnitude of v? And the last one, the derivative of v with respect to the last state of the system should be equal to 0, respecting the controller law, controller norm, the controller form. Okay. So in this case, we are going to employ the higher order neural network into an adaptive controller design. Basically, this is the controller, as you see here. This control law includes the feedback linearization, but in this case include these new terms. These new terms are given by the sliding surface. You can propose your own control law according to your system needs. In this case, for the book, they propose this control law. Basically, if you analyze this control law, you see that you don't know B, you don't know A, you don't know many of the parameters. So your neural network, in this case your higher order neural network, will be estimate all this behavior that we have here in your control law. That's the main idea of the neural network. Estimate the things that I don't know. So this is the update law selected for this specific control law, and this is the input vector. This x of t is this x transpose are the states of the system. The sliding surface over epsilon. This epsilon is a tuning parameter to improve the robustness of the neural network and the controller. And here, this controller and this neural network is bounded by the input and bounded by the omega c subset. In the case of multilayer neural networks, it's also possible employ this control law. In this case, the control law will estimate all these dynamics. If you see, it's pretty similar to that. I go further. It's pretty similar to that law. In this case, our control law has the multilayer neural network that estimates this desired behavior, and we have this UR term. This UR term basically is the noise, the estimation noise of our neural network. With this equation, we can estimate the noise of the system in order to improve the robustness. Here, again, the neural network update laws. We have two layers, so W, V, and the input vector. In this case, the input vector has a bias term at the end. This bias term is required for robustness issues in our system. We can have another control law. In this case, this control law is continuous, but we can include to the control law a variable structure control term in order to get better results. In this case, the variable structure controller for the neural network, the control law is the same that we saw before. And in this case, here we have this UBSC is our variable structure controller. K, phi, and sign of the sliding surface. Here we have the definition of K, definition of phi, basically are the norms of V or the weights. Here the same. And this is our input vector, that is the same vector that we have previously for the multilayer neural network. The update laws, in this case, the update laws are simple, considering that we have this variable structure controller. We can reduce the complexity of these update laws. Okay, but there is another way to estimate these behaviors. In the previous methods, I mean, this BSC, MNN, and HON, basically follow the philosophy of feedback linearization. Cancel all the nonlinearities of your system. This is the main idea for these controllers. But you know that not necessarily eliminating all the nonlinearities help you to improve your control. So in this case, the integral Lyapunov function is a way to compensate some of those nonlinearities and employ the remaining nonlinearities to help you to get a better control. That's the function, that's the objective of this integral Lyapunov function. Here we have the integral Lyapunov function. For this case, again, the system should be in the controller form for apply this design. Basically, in this integral Lyapunov function, we have this term g alpha minus 1. This term is alpha x over gx. Gx in theory is our model, the part of our model, the function that goes with the input. But this alpha we can call a weight function. According to the selection of this weight function or this alpha, we can have a better control or plan or design our own control laws. Basically, this V is weight Lyapunov function for the system in the controller form. Only if you have a smooth function, alpha x, the weight function, that makes that VE will be positive definite and radially bounded with respect to the sliding surface. And in this case, that the Lyapunov function will be, the derivative of the Lyapunov function will be negative definite in all points different than 0. So in this case, we design a higher order neural network using the integral Lyapunov function. In this case, employing the integral Lyapunov function, we can obtain this control law. Here, as you see, this control law depends on G, F, and these terms H1. But all these terms that you see here will be estimated by our neural network, in this case, the high order neural network. So our control action that we will going to apply to our system is KTS plus times EF, the sliding surface, multiplied by W as the structure of the high order neural network that estimate all these equations. The update loss in this case, because the system has the integral Lyapunov function, we need to boundary these final values of our network. So we use the projection algorithm with some modifications in order to improve the performance of the controller. Okay, this is our first study case. This study case is a variable length pendulum system. This is the pendulum, and its length vary according to the value theta, to the angle. Basically, because it's a simulation model, you need the value of A and you need the value of B. So AX in this case is that expression, BX is that one. Here we have the state vector x1, x2. In this case, the x1 and x2 are the position and the velocity of the system. The initial conditions for this system is 0, 0, and that is in addition the equilibrium point of our system. This is the desired trajectory that we want to follow, that we want the pendulum follow. This trajectory is bounded because, as we said before, we cannot extend these controllers globally. And we have, in addition, this disturbance that affects the applied torque to the system. So it's a nonlinear system with disturbance and bounded into a range. Okay. So this study case performed 4 adaptive controllers. The first adaptive controller is using a high order neural network, another controller with the multi-layer neural network, another with the variable structure controller and multi-layer network, and the last one, high order neural network, and using the integral Lyapunov function. All the parameters here are required for our control system. In this case, this lambda is for the sliding surface. This sigma is some of the tuning factors of the high order neural network, the input vector, gamma of omega, in this case is 2, lambda equal to 20 neurons. In the other cases, we have 6 neurons, 10 neurons. The amount of neurons could change according to your control technique. Here, as you see, for the multi-layer neural network, we have an additional input, in this case 1, 1, the bias for our application. And in the MNN, we have gamma for W and gamma for UV, because we have two layers to be obtained. Okay, so this is some preliminary results. In this case, this is in this case the tracking error of the system. As you see, the variable structure controller at the beginning has a very big peaks of tracking error. In the tracking performance, we are going to see why this happened. Here we have a small zoom. After some time, all the errors are stabilized. In this case, this is the error. The variable structure controller, after those peaks, has a lower amplitude than, for example, the multi-layer neural network controller. But in this case, in particular for this system, the higher order neural network, in this case the simples method, has a good response, and the integral Lyapunov function, even without canceling all the nonlinearities of the system, has the best performance. In this case, with the lowest tracking error for our system. So that's good. Okay, this is the tracking trajectory or the tracking performance of the system for all the active controllers. As you see, for example, the VSC controller at the beginning cannot track properly the signal. In this case, the signal is this sine wave. For this reason, if we go back, has these peaks that are consistent with those errors, those tracking errors. After some time, all the controllers will be stabilized, and if we saw that the desired controller is the red one, we can see that maybe in this case the MNN controller has the best performance in this case for perform these tracking control strategies. However, all the controllers are very close to the desired tracking trajectory. One of the most important parts, the convergence of neural network. In this case, as we see, the higher order neural network has a mean convergence. It start and convergence about 6. The multi-layer neural network in this case will take more time to stabilize the weights of the system. In this case, the weights are given by the L2 norm. In the case of the Lyapunov function, we said that we put a barrier, or we limit our controller, in this case, after some time, reach this limit and has a good performance. In the VSC controller, it has a small initial peak, and then has a lower value than the other neural networks. It depends, in this case, of each system, or in this case, each controller. Finally, this is the control action. The control action, the ideal control action will be a sine wave, but because we have the disturbance, we have these peaks here. And as we see, maybe the VSC controller, because it takes more time to adapt to the behavior, has a not very good control action at the beginning of the process. Maybe the higher the neural network has a slightly higher peak, but at the end has a good control performance or control effort. So I'm going faster this part.
Don't worry.
Okay.
Take your time.
So we have non-affine systems now. All the systems that we saw before are affine systems. What it means affine systems? I'm going back a little more. Oh. Affine system. You have separate U from the rest of the state space model, and this parameter could be linearized, could be assumed as linear in some ways, and this parameter is independent. But in the not affine system, you have your states in function of x and u, the both states at the time, the both variables at the time, so you don't have an independent u, and you cannot apply feedback linearization techniques for these kind of systems. And in addition, the output, in this case y, is equal to hx. So it's more difficult to develop inverse behavior response. So, and we don't know f and we don't know h. More problems we have. But with the neural network, we can estimate these behaviors and we can have some good results in that case. Okay, so there are some assumptions that should be due for the system, in this case to design these not affine controllers. The system has a relative degree rho equal to n, so the system should be in the controller form or the normal form. If the system is in the normal form, in this case, the last state should be strictly negative or positive and should be bounded as the same in the previous elements. And finally, the desired trajectory vector is that one and is continuous between the compact set of operation of these controllers. Okay, so in this case, we have the state feedback implicit control law, in this case with a higher order neural network. The idea basically is, if you see u in function of zeta is equal to alpha, a function alpha, in terms of the state variables and the new control input. This is very difficult to estimate or calculate. At least you employ the neural network. This is your new control input for your system. In this case, has v1x, the sliding surface again. We don't forget the sliding surface. And we have zeta in this case. That is our input vector. Our input vector has the states, has the sliding surface term, and the control input that we have. This term v1x, or this term here, we can select this value of this function, that boundary, that term. If we choose one, we have, a not so complicated way to make the estimation. In this case, we can propose this control law, u equal to w estimate multiplied by the basis function in function of the inputs. And here we have the update law. In this case, the update law is more complicated than the other cases because we have the not affine system, so it's more difficult to make an estimation. But these systems has another issue, and in general for most of the nonlinear systems. In this case, we talk about state feedback. We assume that we know the states of the system. But if we don't know the state of the system, we need to use a state observer in order to estimate these unknown states that we cannot derive directly from our model. In this case, basically this output feedback use the state observer, considering that use a higher order state observer, the input vector of the state vector of the system will change. You only know zeta1, chi1. In this case, chi1 is the output of the system, and the other ones are the estimations of the other states. The sliding surface again, this sliding surface, in this case, depend of the estimated vectors. This is our new control input. Here we put this saturation term. This saturation term is important in order to avoid the peaking effect on the nonlinear observer. And this is our new input vector. In this case, this input vector depends of the estimate states. The control law, again, we are using the higher order neural network. And here we are using the control law. In this case, it's pretty similar. We just add this term in addition in order to get more robustness to the system. So, in this case, we're going to study this not affine system. This not affine system has this structure in normal form. Chi1 equal to chi2. Chi2 dot is equal to all those expressions. If you see u, it's combined with other nonlinear terms, so the system is not feedback linearizable. We can apply feedback linearization for this system. Finally, we have y is equal to chi1 to the first state. So those are the initial conditions for our system. This is our desired tracking trajectory. This is the state of the high-gain state observer. In this case, it's proposed by the authors, has 3 states in order to estimate the G2 state. Here, we are going to evaluate the performance of the state feedback controller, measuring directly the states, and using the output feedback, in this case with the state observer. Here we have the parameters of the neural network, sliding surface, number of neurons, input vector. Here, because it's the same neural network, we are going to remain the same parameters for the neural network, and the observer parameters are those ones. Basically, V1, V2 are parameters that you could use to tune the response of your observer, and this epsilon is that determines the speed estimation of the observer. Okay, so we have the tracking error again. At the beginning, both of the controllers are not very good following the trajectory. Then both of them start to get better. In this case, maybe the observer-based controller in some parts is small than the other, but has some small peaks. These small peaks is due to the estimation of the parameters of the system. Here in the zoom, we can see both controllers converge, but this tracking error for sure could be reduced. This is the tracking trajectory. At the beginning, the observer, because it's estimating in addition the state, doesn't have the best fit at the beginning, but after 3 seconds, it starts to perform better the estimation of the desired trajectory. Here, as we see, the state feedback and the observer has a similar behavior, and the red is the desired value. The study case, we continue. In this case, the L2 weights. This L2 weights has the state feedback and the observer feedback. Because the using of the observer, we see more peaks in the estimation with the state measured directly, so the signal is smoother. And the control action with the observer, it will be affected by this behavior because has more stranger peaks in some places, but it's because the estimation. Okay, so some conclusions. First one, the adaptive neural network control provides a framework to deal with different kinds of systems. Systems in controller form, systems not affine systems, even with triangular form systems. Triangular form are MIMO systems. We can deal with those. Using, for regulation and tracking tasks, employing different regionally stable control laws. Regionally stable, in this case, for the moment. These initial simulation results show that the neural networks works very well for the estimation of the inverse response of the system. So it's good to employ this kind of strategies. The integral Lyapunov function gave us the possibility of using not only eliminate all the nonlinearities, but deal with the nonlinearities that works for me to, or can help me to improve the system. The simulation results of not affine systems show that this neural network approximation works, and we can employ this for any kind of systems. Considering that the word not affine, we can say that most of the nonlinear systems are not affine if we go deeper into their modeling. So this technique could be applied to many more systems that we don't have any a priori knowledge of the system. As future works, the practical implementation of this adaptive control algorithm in a system that we don't know so much, for example, fan and plate. We don't have a dynamic model of those systems, or could be very difficult. So it's something that we could use. Some reference, here is the book, where is the book of Dr. Zhang? Oh, here, a stable adaptive neural network control. Thank you, space for questions.
Very good. That's almost 15 minutes. That's a whole book you're trying to cover. Yeah, I think it's a good framework. So my question is, the simulation results you run by yourself,
Yes, I run by myself the simulations.
and you see this is similar to the book one presented.
That one, the first results are similar.
Okay.
The not affine systems
Okay.
has some issues. For example, I don't put in the presentation, but I run the benchmark, the mixer tank,
I see.
the mixer tank, and this tank has a different response.
I see.
But it's not so far from the book, but the response need to improve. Maybe more neurons, maybe different weights or update loss. It depends of that you want to choose.
Very good. Very good. So you use the neural network toolbox
No, I build the neural networks by myself on Simulink.
on Simulink. Is there a neural network?
I have
Yeah, you maybe want to share something.
basically this is another test that I'm performing, but basically it's the same. This is the system. This is the neural network linearization block, even affine, not affine.
Okay.
The sliding surface in this place.
Mhm.
Basically, the neural network is that one. I implement the algorithm, the calculations on a MATLAB function, but this is something tricky for Simulink. The output of these kind of files, you need to split this output with a MUX, and in order to update and integrate, because the update laws are given in terms of the derivative, so you need to make numerical integration to obtain the update W, the update V, or the weights. So, and here it's the calculation of the norms. Basically, this is the norm to calculate. And the algorithm, yes, was built all by myself. Why I have to do it? Because the algorithm itself, I tried to do at the beginning with the MATLAB neural network toolbox, but the update algorithm especially, you cannot change on the MATLAB toolbox. You have to use what they have. In this case, this loss has a stability test, and you need to prove your own stability test.
I see.
This
That's very impressive.
this is I don't know if, no, I don't think it works now. But this is another test that I was running, but it's not working. It's preliminary work. It's not working very well right now.
So I hope you can think about using. Jose showed this neuron stick, so you have a
Yes.
system modeled by neural network, and then controlled by a neural network. So, this is cool.
This is this pendulum is built in MSSC Adams. This is kind of have the pendulum on the real life. Kind of. The idea was I put the rough pendulum I built in Adams. I put the control law itself. I mean, no modifications from the original control laws that I proposed previously. Here is very small range of operation. I mean, it's not working right now. It was a preliminary test that I'm performing, but the idea of this test is if we have the model, in this case, real model of the system using MSSC Adams, it's like has the pendulum in real life, but in the computer. So what happened with those algorithms that works for adaptive performance? I mean, the algorithm, the yellow line tries, but maybe for sure in this system I need neurons, more neurons, because it's the real system. Has frictions, has uncertainties that I don't know in this moment.
I think this gives you enough flavor of neural network control and nonlinear rigorous stability analysis. So I hope you enjoyed it. Anyone? I think the book can be shared. Of Dr. Tao Zhang's book. So it's very clearly written. It's a very good.
Oh, I have to.
It's a very good book to start to learn. Okay. How many pages?
295.
Wow, almost 300 pages. And it's written in 2012?
2012, I think.
No.
2002.
2002.
2002.
Yeah.
Did they do similar examples and show results or not in the book?
In the book, they made a simulation of invert pendulum, but the car invert pendulum,
Okay.
but with a simulation model, not with the pendulum,
Okay.
not with the real life pendulum.
No, the first simulation they asked, not the model.
And also the 3D visualization thing.
Mhm.
It's also very interesting visualization for everyone. Questions? It's been very long for this talk. You use all the Jose's time. Okay.
I'm part of mine.
Okay. Question?
And probably mine, right? Mine was 4:30.
Yes.
Right? Okay.
Also your time. So let's thank Jairo again.